Isotopes and the Mole. I know it sounds like a band, right? Live on stage, Isotopes and the Mole. But it's a little bit different than that. And so I'm going to go through the background. You should have had a lot of this in your lecture. And then I'm going to go through kind of the procedure and how the data will be manipulated. In this particular one, as you're watching this video, I suggest you have the background and procedure open so you can follow along. And also, make good use of your pause button. All right, so let's start off with a mole. And as you know, 1 mole is 6.022 times 10 to the 23rd of anything. That's a 2. Let's write so you can read it. I know it's a weird idea. 10 to the 23rd. And this is Avogadro's number. And it has a symbol, N subscript capital A. And again, remember also that so that's how many of anything. So a mole of paper clips would be that many paper clips, and so on and so forth. All right? And then, so that means, for example, and then there's the atomic mass, or the molar mass, which you get off the periodic table, is the mass, I'll use the eraser again. It's the mass of 1 mole of substance. And again, you should have had extensive stuff about this in your lecture, but that means 1 mole of carbon is 6.022 times 10 to the 23rd carbon atoms. It's also 12.011 grams of carbon. And of course, I get that number from the periodic table. Similarly, 1 mole of lead is 6.022 times 10 to the 23rd lead atoms. And it's 207.2 grams of lead. And so you can do all sorts of math with this. And these are always per mole. So for example, if I was told I had, I don't know, 5.75 times 10 to the 24th, we'll use carbon atoms. And I wanted to find out how many grams of carbon that is. And that's what's beautiful about the mole, is I can't count that many atoms, but I can weigh them. And that's what makes this really powerful. What I would do is, first of all, I have to get to moles, right? I can get rid of the unit atoms using Avogadro's number, so I know that 1 mole of carbon is 6.022 times 10 to the 23rd carbon atoms. And again, this is where your dimensional analysis is going to come in really handy. So the process of canceling units and being very diligent, not just write moles, but moles of what? And then I would use 12.011 grams of carbon per mole of carbon. So molar mass is always in grams per mole. Right? And you see how the units are going to agree. Moles will cancel, and I get grams. And if I do the math here, I have 115, watch your sig figs, grams of carbon. Right? So that's how you do those types of calculations. I know I'm doing them briefly here. Okay, I'm going to erase this, so you might want to hit pause. Similarly, for a compound, if I have, let's say, 1 mole of, let's use, I don't know, Cr2O3. So using a formula, right, that means I have 6.022 times 10 to the 23rd Cr2O3 molecules. I also have 2 moles of Cr. I could use any of these ratios, 3 moles of O. And to calculate the molar mass, a quick review, I have chromium, and there's 2 of them. Chromium is 51, we'll just say 52.00 from the periodic table. Oxygen, I have 3 of them, 16.00. So this is 104. This is 48. So this would be 152. So there's 152 grams of Cr2O3. And so I can use any of these. I'll just do one quick calculation. Let's say that I have 12.5 grams of Cr2O3, and for whatever reason, I want to find out how many oxygen atoms there are. All right, so this is, again, dimensional analysis, right? This is where you really want to watch your units. So I can do this any number of ways. Let's say I want to make grams go away. I know I can use the molar mass, so I know 1 mole of Cr2O3 is 152 grams of Cr2O3. Right? Now, maybe I don't know what step to do, but I know I can get atoms from Avogadro's number. I know there's 6.022 times 10 to the 23rd oxygen atoms per mole of oxygen. And this is a good example of why you don't just write moles, but you write moles of what? See how moles of Cr2O3 and moles of oxygen do not cancel. So what I need here unit-wise is I need moles of oxygen on the top to cancel moles of oxygen here, and I need moles of Cr2O3 on the bottom to cancel that. And I know from the formula that there's 3 moles of O in a mole of Cr2O3. And see, now the units cancel, and I could do the math. So then I go 12.5 divided by 152 times 3 times 6.022 times 10 to the 23rd. I would have 1.49 times 10 to the 23rd oxygen atoms. All right, so these are the types of calculations, and again, your lecture instructor should have given you a lot more examples. All right, again, I'm going to erase this. We're going to hit this. So you might want to hit pause if you want to get a good look at it. Now, let's go kind of through the lab a little bit. So remember, isotopes are atoms of the same element with different masses. All right, or you can say different numbers of neutrons. Because if they're the same element, the protons have to be the same. But if the mass is different, it's got to be neutrons. And again, from your lecture, you should know isotopes have very similar properties. But this is why the atomic masses are not necessarily pure numbers, because the atomic mass, or molar mass, is an average of the masses of the isotopes. All right, and so the average is the percent of A times the value of A plus the percent of B times the value of B, and so on and so forth. And of course, we use the percent as a decimal. So what you're going to do in the first part of the lab, in part A, you're going to basically do an isotope demo. In my lecture, if you saw what I did with the paper clips. All right, so it turns out pennies, we're going to use PE is pennium. And we're going to call pennium 1. That's going to be the so pennies changed their composition in 1982. All right, and then pennium 2 is going to be post 1982. And in the video, we did this, and you can get the masses from the video unless we actually give them to you. All right, and so you can get the masses. And what you're going to do is you're going to take 10 of the pre's and get the mass and then divide by 10 to get the average, because each penny will be a little bit different, right? Then what you're going to do is you're going to take 3 of these and 7 of these, so that this total is 10. So that means this is 30% and this is 70%. And these will not affect your sig figs because you counted them, so these are pure numbers. And so then what you're going to do, you're going to take the mass of 1 penny and the mass of 1 penny, and then you're going to say the average penny would be the percent of pennium 1 times the mass of pennium 1 plus the percent of pennium 2 times the mass of pennium 2. And we even have this, the percentages, pennium 1 is 0.30, and you have the mass, and pennium 2 is 0.70, and then you have the mass, right? And so this would be the mass of one of an average penny. Now again, if you reach into a pile of these pennies, if this pile of 10 pennies, you would never pull out a penny with this mass. Okay? Then what you're supposed to do is calculate, well, what should 10 of this average penny weigh? Well, you would just take this number, multiply it by 10. Okay? And then what we have is we actually took 3 and 7 and we weighed them, and then you can see, well, what did the calculated, you can calculate the percentage error between the calculated and the average. Right? So that's part A of the lab. Right? So hit pause, get a good look at this. All right, let me erase this. Part B is really simple. You're going to take 5, we took some iron, mass of iron, and then we're going to calculate the number of atoms. So we're going to go from grams of iron to iron atoms. And I'm not going to go through how to do this because I did it with carbon, but I did it the other way. But you can do the calculations yourself. Right now, for part B, this is BA. That's a weird number, don't you think? For part B, this is tricky. All right, what you're going to do first, step 1, and I think we did this in the video, and I don't remember if we did it in the video, because I'm writing this before I looked at the video, if we did it in the video, or if we actually if we're going to give you the numbers. But either way, the first thing you're going to do is you're going to determine the density. Now, what we have is a solution that is 64.5% C3H8O by mass. And just to help you with the math here, this means 64.5%. This means that there's 64.5 grams of C3H8O for 100 grams of the solution. So the alcohol is not pure, it's a mixture. So that's what that means. Now what you're going to do first, what we did first is we're going to get the density of that solution. All right? And so density is going to be in grams of the solution. Oops. Let's do this. Solution, I'm going to abbreviate it. Okay, so density, let me erase. The density is of the solution. So the density is going to be grams of the solution per milliliter of the solution. And I think what we did is we pipetted 10 mils in and we gave you the mass so you can calculate the density. But realize that's not the alcohol, it's the solution. All right? Now this part gets tricky, but you'll have this number, okay? Because you'll calculate it. Now the rest of it, okay, get a good look at this because I'm going to erase. All right, so then the rest of it, the idea is this. If you look at the data sheet even, okay, so let's say you work in some weird company and your boss says, hey, I need you to give me I want you to put 1.85 times 10 to the 23rd, 1.825 C3H8O, that's a 3, molecules from that alcohol solution into a cylinder. So that means you got to figure out what volume to put in. So we broke up the steps. So the first thing you're going to do is you're going to take 1.8 to, you try writing all these things. So I'm going to walk you through the calculations. I'm not going to do them for you. You take the molecules and you want to find the grams of C3H8O. Okay, this is on the data sheet. So if you look at the data sheet, all right, then what you're going to do, you can take this number, the grams of C3H8O, and this one I walked through it with a little bit. It's kind of like that first calculation. And you want to find the milliliters, you want to find the grams of the solution. Now the way to do this, I'll help you with this one. From the previous screen, we know that 100 grams of the solution, right, is 64.5 grams of C3H8O. That's the percentage. Okay, then, whatever this number is, you're going to take the grams of the solution, and then from here, you're going to calculate the milliliters of the solution, and you can use the density that you got from that earlier part. Then, the idea is you pour this in a cylinder, and then you weigh it and calculate the percent. You weigh it, right? You calculate this, then we'll actually put some in a cylinder and we'll weigh it. And we'll give you the number of what the cylinder with the solution weighed in the cylinder, and you can find the mass of the solution and compare it to this. But these are the calculations that you're going to do. And it's tricky, but during the Zoom session on the day we're doing this experiment, yeah, I can help you with it some more. All right? So that's part BB. And then the last part, so you might want to hit pause again, is part BC. And you're going to, from part BC, you're going to get the density, and you're going to get it really weird, of air. And what we've given you is we got the mass of a balloon, right? And then we have a balloon plus air. Air is really hard to weigh because you have to weigh a container, but a container is never really empty, right? Balloon plus air, sorry. And then, of course, you can get here, you can get the mass of air. From there, you can get the, from here, you can get the percent, you can get the mass of nitrogen. And you're told that air, the mass of nitrogen is going to be the mass of air times, air is 78% nitrogen, if you look in the lab manual, 78 grams of nitrogen per 100 grams of air. And that'll give you the grams of nitrogen. You're going to do the same thing for oxygen and argon and carbon dioxide. Then I'm just going to walk you through the nitrogen. And you're going to take the grams of nitrogen and you're going to convert it to moles of nitrogen. It's N2. All right, and then you're going to go through and do the same thing for argon, carbon dioxide, oxygen. Then you're going to get the total moles. All right, so from here I'm going to hit pause. So then you have take the moles of CO, total moles of air will be moles of nitrogen plus moles of oxygen plus moles of argon plus moles of CO2. That'll give you the total moles. Temperature of the gas will give you, and then there's a table in your background and you can get the molar volume based on the temperature. The table's given to you, and that's liters per mole. So if you take moles times liters per mole, it's kind of a roundabout way. This would give you the liters of the gas, liters of air. And from the balloon, you'll have the mass of the air. So the density is going to be the mass of air that you got from the balloon over the liters of air. And you calculate that, and then you compare to the accepted value, 1.33 grams per liter. Okay, and again, the molar volume you get from the table, you're going to have to look at the temperature. So for example, if the temperature is 20 degrees, it's going to be 24.068. If you look on and there's a table that has that. All right, that's pretty much the experiment. This one's a little complicated. So on the Zoom session, the day that we meet on this, I don't have the calendar in front of me as I'm recording this. Please, 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 you can ask me questions. I'm more than happy to go through these calculations with you again. All right, so that's all the whiteboard discussion for this. So I'm going to go ahead and end this video, and we'll talk about it when we're in class. It's got a little bit of calculations, like I said, but I walked you through it, and hopefully you can do it. And if you can't have trouble, that's what office hours and the Zoom sessions are for. All righty, take care.